Yes, we continue with discrete Markov chains as we continue with the stochastic processes playlist. And here we look at absorbing Markov chains. Of course, we've talked about absorbing behavior in the last video, and we've seen the possibility of absorbing states in different transition matrices in previous videos too. And now let's look into absorbing Markov chains with some more uh, closeness. So an absorbing Markov chain, of course, is a Markov chain in which at least one state is absorbing, and the indicator of that is that you see that one of the rows has a probability of one somewhere. So every state can eventually reach an absorbing state in that case. So the definition is that a state I is absorbing if PII is equal to one. That is, if the probability at maybe row one column one or row two column two or row three column three, the probability of moving from a state to itself is guaranteed as one. That is when you have an absorbing state. So this means once entered, the process never leaves that state. Okay. So we now have example of states, right? So consider state zero. Let's say that is game over, which is absorbing. So when the game ends, it ends, right? Then you now have state one playing, state two playing. But if you reach state zero, we stay there forever because when the game is over, that's all, except you want to start playing afresh. Okay. So we have the canonical form of transition matrix. The canonical form of transition matrix is like this. So you rearrange the states. So absorbing states come first. So in this case now, I is identity matrix for absorbing states, and this is zero here. Then you have Q, which are the transitions among transient states. And you have, so Q are the transitions among transient states, and R talks about the transitions from transient to absorbing states. So R talks about transition from transient to absorbing states. So identity matrix, that's absorbing states. So typically an identity matrix is an absorbing state, as you can see. In every, I guess I need to write now. So because absorbing state is, okay, imagine for a 2 by 2 matrix, which you use mostly, you have 1 0 0 1. So that means if this is state one and this is state two, state one to state one, state two. So it means the probability of moving from one to one is equal to one. So this is P11 and this is P22. So that means once you move here, you're stuck, right? So all these unit matrices, they indicate absorbing states, no matter what the dimension of that matrix is. Then you have that. Then you have R, that's transitions from transient to absorbing states, and you have Q, that's transitions among transient states. So things are still cool in Q, but in R, you're moving to that I, and once you get into I, you're trapped. So we have a fundamental matrix here now. The fundamental matrix is defined as N, which is equal to 1 minus Q raised by minus 1. So that means the identity matrix, the absorbing states minus the transitions among transient state raised by minus 1. That gives you N. And the interpretation is that Nij, that's the expected number of times the chain is in transient state J, starting from state I. That's what that N is about. That's the fundamental matrix. And then we have expected time to absorption now. Expected time before you get into the absorption state, you know, into the absorbing state, right? So T now is n dot one, where dot one here is column vector of ones, right? That's the fundamental matrix multiplied by ones. That gives you the absorbing state, expected time to get into the absorbing state. And interpretation is that T sub I is expected number of steps before absorbing, starting from state, before absorption rather, starting from state one. And then we have absorbing probabilities. So for absorbing probabilities now, we have that B, you have this B equals N dot R. B equals N dot R. So the interpretation is that Bij is the probability of being absorbed in absorbing state J, starting from transient state I. So what's the probability if you start from somewhere, you are going to get absorbed in the absorbing state? So consider the transition matrix P, which is 1 0 0, 0.5, 0.5, 0.2, 0.3, 0.5, right? Clearly, state one is absorbing, right? Or if you call that state zero, anyhow you want to call that. Okay, yeah. In here it has been called state zero. So state zero, state one, state two. So in this case, now that's like 0 1 2 0 1 2. So you see that state zero is absorbing, whereas state one and two are transient. This is transient and this is also transient. So if you want to extract the matrices that makes that happen now, you have your Q. Q is the movement among the transients. Okay. So no, R is the movement among the transients. What's that again? What's that Q now? Let me get back. Transitions among transient states, yeah. And R is transition from transient to absorbing. Okay. So here now, based on this P, we then have Q to be 0.5, 0.50, okay, that should be this corner now. This corner, that is your Q. Transition from among transient states. So you have 0.50, 0.3, 0.5. But this R now is 0.5, 0.2. So now this talks about probability that you're going to move from state 2 to state 1 in that 0.5. So this is probability that from state 2 you get absorbed from state 3 from state 1 rather, because it's 0 1. So state 1 to 0, state 3 to 0. So probability you're going to move from state 3 to 0 is actually to state 0 is 0.2. So R now is moving from transient to absorbing state, and Q, this corner is movement from movement among transient states, basically. So you can extract your Q and R like that. So, and with that, now we can have this matrix. So you have, so you extract Q, Q is 0.50. That's this corner now. 0.50, 0.3, 0.5. That's what we have here. And R is 0.5, 0.2 right here. So when you run that, you have 1.22. So these are the expected values here, this absorption probabilities also. So you have two, okay, these are expected values, I believe. So 1.22, like that. So expected time absorption now. So the time to absorption is, so it means you now add everything. So that's 2 and 3.2. So the time it will take to get absorbed, you have these 2 and 3.2 like that. Okay. So this is like time to move from one to one is 2. Time to move from 1 to 2 is 0, because you don't ever get there. Then time to move from 2 to 1, or I'm mixing up this 0 1 thing a lot. So yeah, time to move. Okay, yeah, let's just go on. And then at the end of the day, expected time to absorption will now be 2 and 3.2. Then we talk about the absorption probabilities too, which is n times r. So here you have the probabilities are 1 that they are going to get absorbed, guaranteed, based on what we got as b. What is our b somewhere? B is n dot r, right? B is n dot r. So B here is n multiplied by that r, and we have 1.1. So that's guaranteed that they're going to get absorbed. So interpretation of result. Matrix n shows how long the system stays in transient states. Vector t gives expected time before absorption. Okay, so vector t gives expected time before absorption. That's 2 and 3.2, like that. Then, so this is vector n right here. So that's vector n. Vector n shows how long the system stays in transient states. So, so then lastly, we have matrix B, which gets probabilities of ending in absorption. So that's guaranteed absorptions is what we have from all of this now. So we can look at this whole idea in terms of gambler's ruin problem. So a gambler can either lose or win, and loss a lot, either winning or losing are absorbing states. But in between, you have transient states. So if 0 is lose and 4 is win, that means 1, 2, 3 are transient. So you can move from you are still playing from between 1 and 2, 1 and 3, 2 and 3, and all that. So, but 0 and 4 are absorbing states. So these are like limits. They are like boundary values, so to speak. Losing or winning are boundary values. So at each step, you can win with probability P and you can lose with probability 1 minus P. If that is the case, then we have this code to drive that point home. So if we say probability is 0.5, so if you have equal chance of winning or losing, then Q can then be 0p0, 1 minus p0p, 0 minus 0 1 minus p0, and R is 1 minus p0, 0 0 0 p. And then we can calculate n. N again is the matrix which shows how long the system stays in transient states. So this tells us 1.5 in transient states, 1, 0.5, and all of that. Then we have the expected time before absorption, which happens to be the addition of everything in each row. That's 1.5 plus 1, that's 2.5 plus 0.5, that's 3. 1 plus 2 plus 1, that's 4. Then 0.5 plus 1 plus 1.5, that's 3. So that's expected time before absorption. So you expect that this takes three time units, whether it is second or minute or whatever it is you're considering. So you have 3 4 3 like that. That there's the expected time before that's each state is absorbed. Then you have absorption probabilities too. So in that case, now you have n multiplied by r. So that's 0.75. So the probability that this will be absorbed is 0.75 and this is 0.25 and so on and so forth. So the key takeaways from all of this is that absorbing states satisfy PII equals 1. And that is why all unit matrices are absorbing, have every state in a unit matrix is an absorbing state, right? Because P11 is 1, P22 is 2, P33 is 1. Sorry, P11 is 1, P22 is 1, P33 is 1, and so on and so forth. Then you can rearrange matrix into canonical form. Canonical form is that place where we identify R, Q, and all of these things. So where you have I, the absorbing state, you have 0, then you have R, that's the probability transitions from transient to absorbing, and Q, that's transitions among transient states like that. Then we then talk about we can compute n the fundamental matrix. We talk about the time to get absorbed and the probability of getting absorbed. This allows us to fully analyze absorbing Markov chains. So if you're interested in absorbing Markov chains, you can consider all of these ideas. So we have some practice problems. Determine the following okay, here we have 1, 2, 3, right? Determine whether the following matrix measures an absorbing Markov chain. Absolutely, because once you see one, that's an absorbing absorbing state right there. Identify the absorbing and transient states. The absorbing state is states. If you call it 1, 2, 3 or 0, 1, 2, the absorbing state is 0. If you call it 0, 1, let's say it's 0, 1, 2. So state 0, state 1, state 2. So state 0 is absorbing, state 2 and 3. I mean, state 0 is absorbing, states 1 and 2 are transient. Okay. So for 3 now, write the canonical form of the transition matrix. Of course, the canonical form would be so you have okay. The canonical form will have to be you have to identify the of course this state 2 is absorbing for sure because P22 is 1, so it's absorbing. So to write movement among transients will have to be, I guess I need to write this out. Yeah, I need to do this. Let me do that. I think it's really important to take care of that. So I copy this then and take it to the worksheet. Yep. So now this. So based on what we have learned already, right? We have so we have this now. This part is absorbing. So it means that movement along transients, which is Q now, will be so you see this 0.5 and 0.3. Okay, let me even do it this way. Let me do it this way. So let me name the states so it can be easy for me to talk about them. So we are saying that okay. Of why all this back and forth? Yeah, good. So we're saying, let's say this is state 1, state 2, state 3. This is state 1, state 2, state 3. Okay. So 2 to 2 already tells us absorbing. So here we already have that state 2 is absorbing. Okay. Because P22 is equal to 1. Probability of moving from 2 to 2 is 1. So get that is established. Then next, states 1 and 3. States 1, 3 are transient. Okay, they are transient. So if we need Q talks about the transient states. So Q now is going to be so this is still transient, transient. This is not transient, by the way. This is transient. This is transient. This is transient. So in that case, now we can say that Q, which talks about movements between transient states, is 0.50, right? And 0.2, 0.5, 0.2, 0.5. Okay. So that's talking about the transient. But for absorbing, so moving from 1 to 2, you know, is probability of moving from 1 to 2 is now this one, 0.5. Moving from 3 to 2, that's 0.3. So it means that our R is 0.5, 0.3. So R is 0.5, 0.3. Okay. Yeah, so now this is movement, movement between transient states, between transient states. And now this is movement, movement from transient, transient states, from transient states to absorption states, to absorption state. And that goes. So that's what we have right there. So that's trying to write that in canonical form. So now, okay, 4 to 6, try your hands. Or maybe I can show 4 to 7 at once. So try your hands, 4 to 7. Expected absorption time. Already, okay, I mean, expected absorption time will just be addition. That's 3 and 2.5, basically. Then, yeah, so try your hand on all of these things. So absorption probabilities now. We need to get so I think that's n dot r. I just multiply the two together and you're good to go. Then yeah, so try your hands on all of these things. So you have all this, you want to compute n, you want to compute all of that. So just follow the definitions and you get the n computed. Okay. So with this, I come to the end of this interesting video about absorption Markov chains. So don't forget the formulas. Here the key things are the fundamental matrix, which is I think I minus Q inverse. So so n is I minus Q inverse. You already know I is identity matrix, Q transitions among transient states, and R is transitions from transient to absorbing states. So to get n now, so if you know identity matrix and you know your Q, you can get your n from that. And once you get n from that, so once you get the n, you can then calculate expected time to absorption, which is still as n dot, the matrix of ones. Maybe I should even do that with this matrix I just worked with. And then B is n dot R. And with that, so that talks about the absorption probabilities. Okay. So I guess I want to do that with this one I'm working with now. So n is 1 minus Q inverse. Hope that won't be too much work though. N is I minus Q inverse. Okay, maybe I'll just write down the formulas. Um, maybe I should just write down the formulas. So the fundamental matrix, which is the expected number of times the chain is transient, is in transient state J, starting from state I, right? So expected number of times the chain is in transient state J, starting from state I. So now we know that N, 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 N is equal to I minus Q raised by minus 1. Okay, so that means we just have that to be we already know I is the absorption, right? So that's 1 0 0 1. This is 2 by 2 here now, minus Q. Q is 0 0.5 0 0 0.2 0 0.5. So all this raised power minus 1. So I won't complete it because taking inverse. Okay, I think well I won't just complete it. You can just deal with that. So 1 minus 0.5 is 0.5. 0 minus 0 is 0. 0 minus 0.2 is minus 0.2. 1 minus 0.5 is 0.5. Take the inverse of this and you get n. So once you find n, the next thing is you need the time. So time to get absorbed. Time in that case n dot 1. That's matrix 1 now. So this one now is now this 0.5, this 0.50 minus 0.2, 0.5, inverse multiplied by 1, 1 like this, and you get your result there. Then you get B, probability of absorption. That's N dot R now. So N dot R, so the same N here, that's 0.5, 0 minus 0.2, 0.5 raised power minus 1. That's that inverse. Then R, the R you already have from here, which is 0.5, 0.3. 0.5, 0.3. Okay. Well, even if I don't use, I can just find these inverses, right? Using maybe using Wolfram Alpha. Maybe let me go. So instead of just computing, let me just use Wolfram Alpha and we are good. 0.50 minus 0 to minus 0.2, 0.5. Okay. So let's go for Wolfram Alpha. Wolfram. Yeah. So I have 0.50, comma, minus 0.2, and 0.2, 0.5. Hope that's correct. 0.50 minus 0.2, 0.5. Then we take the inverse of that. So raised to power, that's raised to power minus 1. Okay, I think that's not working. So I don't need these brackets. That's what this tells me. Yeah, so we have all that. And that gives okay, that's 20, 0.82. Okay, 20, 0.82. So this is 20, 0.82. Okay, that's that there. And then we can then multiply that by 1, 1. So we have quickly 20, 0.82 multiplied by 1, 1. That gives the time, right? So that means we have 1, 1, 1, 1, because we have two rows there. That is 20, 0.82. So that means we have uh 2, 2 up here, and then 2.8 here, 2.8. 2 and 2.8. So this whole thing is 2 up here and 2.8 down here. So that goes. So that is that. Then for NR now, again, that is 20, 0.82. That's 20, 0.82 multiplied by 0.5, 0.3. So that means we have so write this twice again, 0.5, 0.3, 0.5, 0.3, put 20, then put 0.82. So that is 0.5 times 2, that's 1, plus 0, that is 1 here. Then 0.5 times 0.8, that's 0.4 plus 2 point, 0.4 plus 0.6, 0.4 plus 0.6. That's also 1. Okay. So the probability that of absorption is guaranteed. So 1, 1 in each case like that. So that's so with that, I've taken care of all the all the possibility, all the possible questions. So if you have any other matrix, you just follow all the steps there. So again, don't forget, try your hands on the questions. 1 to 4 there, 5 to 8 here, then 9 to 13 is 9 to 12, say 9 to 12. Then you have 13 to 15, maybe 13 to 15. Then you have 14, 16 to 20. Okay, oh yeah, 16 to 20. So that's the end of this interesting video about absorbing Markov chains. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, I'll tell you, go ahead, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, and that gives you some special privileges like getting to see some videos first or seeing some videos exclusively, because you're a member of the channel. You can also request for PDF copies of my notes or hang out with me to discuss anything that interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.